So let's take a look at the next problem. Application is slow. We get this call day in and day out, right? And something is slow, application is slow, it could be the network, it could be congestion, it could be a lot of things. So there are things that you can do with nothing but packet trace to rule out certain things, okay? And your job as doing protocol analysis is to definitively rule out, and this is how I'm going to segue into Dr. McCann's presentation. If you know this part's not even being touched, get rid of it. That's not part of your problem. Concentrate your efforts on something else that you know you can't rule out, right? So let's do that. When an application is slow, what are some of the usual suspects immediately you should think about and rule out? Long round trip time. Not a problem in and of itself, but it can lead to other problems, which are bandwidth starvation, okay? We call it BDP, bandwidth delay product, right? Basically, you're trickling, you got this massive pipe, and you're trickling water through it, and you have to wait till it gets to the other side, and you're not using your full available bandwidth. Very common problem, okay? What else?
Large deltas?
Large deltas is a problem, right? So typically, what you do is you scroll down and just kind of scroll through this, and I actually do it at this speed. And what am I doing? I'm just letting my brain pick up on things. So as I'm doing this, what did you guys see? Anybody? So there's a huge delta there. That's a problem. What else? Is it always a problem when you see a huge delta? When is it not a problem? User think time. If I'm sitting there hovering over the mouse, TCP has nothing to do. It may or may not be a problem. You have to actually interview the user to find out. And there are other clues to this. What else is going on? What else did you guys see?
Second sauce.
I'm sorry?
TCP second sauce.
TCP.
Second sauce.
Okay. What do we see about the length here? You're talking about this here, right?
Yeah.
Okay. What does it show? What is it telling us? Anything?
Well, one system using an MTU of 1500 bytes.
Okay.
The other one, assumably 1400 bytes.
Okay. So we got 1400 here, 1500 here, 10 here, 1500, 1500, etc.
I'm talking about the maximum second size used.
Okay.
So I would look at the three-way handshake to determine if they agree on really the lowest number.
Okay. So here what it's talking about is the maximum segment size. This guy seems to be using 1360. The other guy seems to be using 1460, the default. Okay? But let's say you didn't pick up on that for now. No. This is a legitimate question. Is it a problem? Right now, do I need to worry about that? Why do I not have to worry about that as a problem? Because packets are going through. If there was a huge problem, communication would come to a halt. It's not coming to a halt. So I'm going to classify that as something to look at, but maybe not right now. Okay? Things are slow. What do we type? What's the first thing that we always type? And actually, you should have picked up on this already, but I'm going to show it to you. Wireshark makes it very easy. What do we see? Are all Windows updates bad or evil?
No.
Okay. Windows update means what? For example, this guy, what does that mean? My window used to be smaller, but now I'm letting you know I have a bigger buffer. You can send me more information. Is that good or bad? Doesn't matter. Not good or bad. Just means I've used up my buffers and now I'm free again. When does it become a problem? And what does zero window tell us? Stop sending me data. I can't deal with this I don't have buffer big enough to deal with you right now, and it's throwing up a stop sign. Whose problem is that? The network? I'm sorry? The host that sent the 0 window is the problem, right? And who sent it? And in my packet traces, 192 is always the client side. Is this a server problem or is this a client side problem? Client side problem, right? So when you first saw this, and I'm gonna actually get rid of this. When I got this packet, this is what I did. I was scrolling down and a block of text scrolled past, and I said, whoa, wait a minute, stop, let me take a look. And I go back, and I did that, right? Now, why don't I just type TCP analysis.flags? Because I'm stubborn. And it's also training. It's training your eyes to pick up on different patterns. Wireshark can't tell you everything that's wrong. Sometimes you have to pick up these patterns on your own. So the more you do it, the better you get at it. So don't always depend on the tool, the analytics of the tool. If you can, and you have the luxury of time, sort by the delta column and scroll down and see if there are bunches of deltas that are of same value, 200 millisecond, 150 milliseconds, 100 milliseconds. These are signatures that you can use to look at delayed act problems, for example. Okay? So there are different ways to see this problem, to visualize this problem. The first way to do it is you can look at I/O graph. All right? And when you open up the I/O graph, oops, come down to here and click on Advanced. And whose problem did we say? Client-side problem. So whose window size are we interested in? The sender or the client? Or the receiver? The receiver of the data, right? Because the receiver is the guy saying stop. So who was the receiver? I'm looking at only sourced from 192.168.1.1. And what am I looking for? I'm looking at, what am I interested in? Window size. And I'm going to say graph it. What do we see? Typical jigsaw pattern. Up, down, up, down, up, down, up, down. Now, right here doesn't mean that it's at 0. It's kind of like Excel, right? It just means there could be no value, right? But when you see these peaks and valleys, these jigsaw-like puzzle, it's telling us we have a problem, may have a problem. Another way to visualize this. Let's apply this as a column. Okay, here's the window size, only sourced from 192.168.1.1. And as we scroll down, so far so good. What happened there? So this column right here is the window size. And the fact that window size is going down, is that a bad thing? Not necessarily. I mean, that's what buffers are for, right? It becomes a problem when it becomes so small that I can't receive any more information. That is a legitimate problem. And it has nothing to do with the network. If anything, the network is sending you too much data. Okay? Another way to visualize this is to look at my favorite, which is Stevens graph. And these are things that I do all the time. I look at Stevens graph, and I zoom in, and what do I see here? Stevens graph is nothing more than, over time, how many bytes I've sent. The more steep the slope, the better, because it just means that I'm sending more data over time. When I see patterns like this, though, it concerns me a little bit, meaning I have a sudden, large amounts of data going out, and I plateau out, I send, kind of plateau out, send, plateau, send, etc., right? It's not a, so for example here there's a huge plateau where it's flat. I want to kind of see a consistent line going straight up, ideally. Not everybody will, not every graph will look like this, but ideally that's what you want to see, a 45-degree angle just kind of going slow and steady and increasing, right? More bytes are being sent over time. So this is another clue that I have a window problem. Looking at windows here and scrolling down is another way of saying it. And another way to do it is by doing the charting functionality. Okay? So what was the culprit? A/B scanner. It was a script scanning, and this website had a lot of scripts built into it, and the way with JavaScripts and etc., it's kind of a choke point. You can't do anything else until that script finishes processing, and when the antivirus is scanning for that, everything else on the web page has to stop, because even though you might have other TCP sockets and open, etc., with JavaScript, you have to stop and process it and wait till it finishes, so everybody kind of chokes up behind it, the web page slows down, and that was our problem. So what did this tell us? How much time do we have, by the way? Is it about 20 minutes? Okay, perfect time. Okay, perfect. So this is telling us that it's not a network problem. MSS, it's different. Okay, put that away. Not interesting for now. Packets are getting through. TCP window size, a big problem. But whose fault? Client side. Is it an infrastructure problem? No. And so then you can tell, and you can rule out this massive infrastructure that you have. You can rule out the server, the load balancers, and then everything in the middle, and you concentrate your troubleshooting on the client. And that's what we did. And there are only a few things that can mess up communication on the client side. Wrong drivers, virus, and duplex mismatch. That's pretty much it. Is this a duplex mismatch problem? How do I know that? It wouldn't work well, but from a packet analysis standpoint, what would I see? Retransmissions, because packets are getting lost. Okay? I don't see that here. What I see is a PC that can't deal with the amount of information that it's getting. So it's either a faulty driver, old, outdated driver, or a machine that can't keep up. Okay? And so by doing troubleshooting on the PC side, we were able to figure out that it was a it was an antivirus problem. Don't sue me. Don't sue me. It was an antivirus problem. All right? Okay, any questions about this one? Again, in and of itself, none of these traces are very exciting or complicated. But what I'm trying to get to, though, is ability for you to kind of divine information that's like circling around these packet traces. Okay, and it's your job to go to that next level and start to pluck this information out and guide people in the troubleshooting. Okay? Just from nothing more than packet trace. All right, so this next example is pretty fascinating. It's titled Internet is the Internet. So I don't know about you guys, but I do a lot of internet troubleshooting. But if you look at a lot of the carriers, their packet loss SLA on the internet is pretty high. 1 to 2 to 3% packet loss from a contract language is not unusual. It's never really that high. But how do you troubleshoot? How do you begin to troubleshoot the internet? A lot of times you don't. You just punt it and say, I can't help you. It's the internet, right? So this is somebody on my team, Tom. I was busy. I got an email and I said, hey, Tom, can you help this guy out? And he called me and said, yeah, it's the proxy and the internet. What do I do? I said, Tom, just quickly triage it and then punt it. That's exactly what I told him. Triage it and punt it. It's the internet. What can you do? So he says, okay. So then he calls me back and says, guess what? Not the internet. So this is the problem that we got. A business unit within Citi has their own respective customers, right? So my customer is the business units within Citi. All the different technology, investment banking, Citibank, Citi Financial. These are my customers. So this customer, a unit of Citi, dealing with you guys, external customers. And they're saying that this platform is extremely slow. And they're not happy about it. And it traverses the internet. So that's why I said it's the internet, what can you do? But Tom found something that was actually pretty fascinating, and it's a perfect example of knowing what to look for, when to look for it, to zero in on a problem. All right, so let's look at the evidence. So there are a couple of things that we learned throughout the session. The red-headed stepchild of protocol analysis is the IP header. It can be a big clue, kind of like the Blue's Clues thing going on, right? It can clue you in to a big problem, or it may help you rule things out. So immediately something should jump out at you when you look at this. 16-second delta. Is that a problem? Could be. I don't know. Maybe there's think time going on. So what do? We called them up and said, hey, how does your application work? Well, the user clicks on it, gets the data back, and it refreshes the page. Anything else besides once they click? No. Okay, so we ruled out user think time as a problem. Now we have a legitimate problem. But it's the internet. What are you going to do? Right? I'm sorry? Call Al Gore, yeah. Call Al Gore. So one of the things, I'm going to kind of digress here and go down to and give you a big clue. So in the IP header, there are a couple fields that are very important, or can be very important. One of it is IP ID, like we talked about, right? And IP ID helps you identify what? I'm sorry? Whether the system is busy or not. It's a big clue into how many clients is this IP stack servicing from a TCP standpoint or UDP. Okay? TTL is another one that's kind of interesting. TTL can mean, and it used to, if you read the RFC, it says decrement by clock, 1 second, half second, etc. And then people quickly realized that's not going to work. So they took the easy way out and said every hop on a router decrement the TTL. Why did they do this? They didn't want packets flying around the network forever. So when it decrements down to 0, then you get a port unreachable or TTL expired message, and the packet dies. And then someone cleverly figured out traceroute using TTL expiration. So here are some of the values that you see on a TTL. Why is this important? It can kind of clue you into what systems you may be dealing with. Okay. The other thing too is these numbers should be pretty familiar to you, right? You don't have to memorize it, but it's 30, 64, 60, common numbers, right? Do you see any number here that says 13 or 27, 24, like that? No, right? Nothing exotic there. So let's look at the packet trace. So let's think this through. Fundamentally speaking, right, what's the chief complaint here? Sorry? It's slow. We already figured out there's no user think time. So this legitimately is a problem. So what happened between packet number 5 and packet number 6? Sorry, let me open up the other. Okay. So it says sequence number 1, acknowledgement 412. What does that tell us? One more time? Okay, 1010 hasn't sent anything yet, right? I did, however, see 412 bytes from the other guy. Okay? And this is the first time I'm seeing a packet coming in. Okay? So when we first look at this trace, some things you should immediately zoom in on. Here's the SYN and SYNAC. The delta is about 140 milliseconds. I know geographically what I'm dealing with here. It's certainly not New York to Texas. It could be New York to Europe, right? Because 140 milliseconds, as you do more and more of this, you realize North America to Asia Pacific, 250, 300 milliseconds typically. To Australia, 275, 300. Okay, these are some numbers that you kind of pluck out over time. So I'm dealing with, all right, this is North America customer talking to probably somebody in Europe. Okay, I don't know that for a fact. Well, actually I do, because in real IP, I can just go to Aaron or Ripe and type it in, right? So I knew that this was EMEA, but I didn't have to actually, I don't need Aaron or Ripe to tell me that. I can tell just by looking at the round trip latency. Okay, what else? Could something have happened from here to here? I'm capturing it from 192 side. Do I know if 10's been trying to send me packets? For all I know, this could be the mirror image of the other earlier problem where somebody was sending me packets and it just got stuck, black hole. How do I know if this between here and here that this guy wasn't sending me packet after packet after packet after packet trying to talk to me?
Look at the IKD.
All right, so let's do that. And what is that going to tell us? I'm sorry? Okay, so I'm going to add the IP ID here, and something should become immediately apparent. Or maybe not. Window size? Oh, I'm sorry. sorry. Oh, I do have it right here. Okay. What happened between this packet and this packet? Was there a retransmission going on? Was the 10-dot guy trying to reach out through the cloud and touch me? Nope. Is that 10-dot server particularly busy? So this is a commercial server with a vendor doing nothing but talking to me. What are the chances that a site like Amazon has no other customers but me? And this is what it's telling me.
Good service.
Yeah. We're sitting, damn it. Dedicated server for one guy. So actually, there could be a proxy in the middle, right? Even then, IP stack tends to be what? Communal, right? Even on a proxy and a load-up balancer, IP stack is common to multiple TCP stacks. It's like a funnel, right? So what do I know from this trace just by looking at the IP ID field?
You're not dropping packets.
I'm not dropping packets. There was nothing going on between this packet and this packet. So whose fault is it? The server. How do I know that? Because at this point in time, the server was doing nothing. He wasn't talking to another customer, another application. Nothing was going on this server between this packet and this packet. And my proof positive, this packet and this packet, and my proof positive is that IP ID incremented by just 1. Nothing was going on. This is all server processing time. Okay? So once you're armed with that knowledge, what do? You call them up. Hey, your server's broken. It's not the internet, right? And when we call them, the irony was we had configured to talk to its old UAT system, meaning its test system. So they've migrated off this platform and went production somewhere else, somewhere close, actually. And we didn't get that memo, apparently, and we were using the old system that no one else was using. So when we called up the vendor, they said, what address are you going to? And said, you know what? We migrated off that months ago. You should be using this system. So all that time, we were paying needless delay, and it took someone to finally pick up the phone and say, something is wrong. And I give Tom from my team credit. I punted it, said, it's the internet, triage it. He did. But when he looked at this, most people will say, oh, it's either packet loss happening from here to here, or it's a delay, and maybe would have punted it. But what he did was he looked at the IP ID field and TTL to figure out what was happening. And why is TTL important in this case? What's my TTL here? 62. 64 is a common number, right? I just showed, and 60 is a common number. So if I'm thinking 64, maybe 128, I'm probably, if it's 64, I'm just 2 hops away from the capture point, from the server. Okay, so when 192 sent it out, he probably started out with 64. Okay, I know it's not 128 because this 192, 168 is on my network. And I know it doesn't take 64 hops to get out to the internet. I know that because my network, right? So I'm probably just 2 hops away. What about this guy? What's his TTL? 44. So he probably started out around 60 something and went through 20 different hops to get to me. Nothing unusual. Hop counts mean nothing from a performance standpoint in modern day network. Just to get out of my data center, I can go through 8 hops. Just to get out of my data center. It doesn't mean anything because it's all hardware switch. Back in the days when packets were process switched, TTL did mean something because the routers were literally could add milliseconds in packet processing time. Here, they're done in microseconds, and so it's nothing to worry about typically. Okay. So what's the lessons learned here? Look at the IP ID field, and before you punt, do a quick triage. Don't throw away the IP header. I know it's not exciting, and most people that do Wireshark analysis are always in this TCP field. But IP ID has a wealth of information that you can use to rule things out. Okay? Any questions so far? Okay, I think my time is up, is it not?
7 minutes.
Oh, 7 minutes, okay. So let me go back to, by the way, any questions here about Wireshark using the column? The one other thing that I want to show you before we get to the things that I do, I use profiles here. And the reason why I use profiles is because when I'm troubleshooting, I want to be able to see different layout quickly, back and forth. And one thing that I do have is absolute date. So why is this important? So a friend of mine is in med school, and the analogy here is this. She was doing the, going through, not nuclear medicine, but x-ray, looking at x-rays and whatnot. And the exam was, the first thing you do when you look at an x-ray, what do? I'm sorry? When was it taken and who was it taken for, right? Because the worst thing you want to do is look at the wrong x-ray for the wrong patient. So the first thing I do, I look at the absolute time date stamp. Make sure that somebody didn't give me the wrong packet trace. Nothing ticks me off than spending 2 hours saying, you know, I'm not seeing anything here. Oh yeah, sorry. GMT offset, you're 2 hours away from the problem. So I quickly look at absolute time. Now I can do that by looking and changing the time field here, right, the view. But I just got used to doing it this way, so this is what I do. Some of the other thing that I do one where I just have the time, because the reason for the absolute time and not the date is once I verify the time, some users report problems in real time, like at 9:15, right? Or when you're working with a chronic problem, you train users to say, hey, look at this clock here. When you have a problem, see what time that is, because for the most part, we're synchronized. And at least that gets me in the right ballpark. I may have 100,000 packets in a second, but it's better than 1,000,000 packets. So at least get me in the right ballpark. Okay, so this real time, the timestamp here can be important. And actually in my next session that I'm doing, it was one of the first clues. It helped that when the user said, I had a problem at 9:17, it got us there quickly and we were able to find the root cause. Okay. The other thing that I do is, I don't have it here because this is the new Windows 7 build that I have. I haven't had time to do it, is I turn on relative sequence numbers. And so the reason why relative sequence numbers are nice is that if you haven't seen it, TCP sequence numbers are what kind of numbers? It's a 32-bit number, pretty large. So instead of looking at 412 versus 1, if I look at a real TCP real sequence number, that 412 just became this number. And of course there are no commas here, so you have to sit here and go 774, 740, is it 1.2 million, 12 million, 1.2 billion, I don't know. No commas. My pet peeve. When you're looking at an interface stat on a router, no commas. You have to literally sit there and go, well, okay, is it 12 million, 12 billion, 120 million? Anyway. So it's difficult. Your brain has hard time processing these large numbers, so relative sequence numbers are good to use. When should you not use relative sequence numbers? Capturing at different points, perhaps. Different start times, because relative means just that. It's relative to where you started your capture. May not line up. So when you're looking at specific gaps in and transmission, sometimes it's better to be sure by going to real sequence numbers and looking at it from both sides. Okay? Also, if there's NAT in the middle, sometimes, depending on how it's being NATed, sequence numbers may get jumbled, it may survive, IP ID may survive. So over time, you're going to develop these practice and patterns and habits where, even though I know it's going through a firewall or a NAT, you're going to realize, oh, you know what, big IP tends to only munge the source sequence number, not the destination, or it maintains the IP ID, and you'll start to pick up on these combinations to help you troubleshoot. Okay? So again, nothing that I showed you in this class was really elaborate or difficult problem. What's difficult is trying to get as much information out of it, and if you know what you're doing and you practice, you can rule things out. It's all about dividing and conquering. Right? We all have a lot of things to do. Divide and conquer. Reduce that problem set to something that you know for sure you should concentrate on, and throw out all the other clutter. Okay? And the more you use this, the more your brain's going to be able to quickly rule things out, and they just kind of disappear in the background. And different problems it'll be like a shining beacon, if you will. Okay? And that's kind of what you need to do, and you can only do that by practicing. Okay? That's all I have. Any questions for me? Yes. Okay, so what other tools do I use? We actually use different tools from both Pilot. When I'm dealing with huge trace file, Pilot, if you haven't seen it, I encourage you guys to download Pilot demo and take a look. It's the GUI version of the Pilot, the way the concept of dragging and dropping these analysis to the packet trace file is phenomenal, right? So we also use OpNet, ACE Analyst. A lot of the problem, though, is we all suffer, or all these tools suffer from garbage in, garbage out. And so you really do have to be diligent about, it's nice reports that gets, it spits out beautiful looking reports, but it may all be based on false information, and it turns out to be useless. Okay, so it's your job as analysts to rule that out and make sure that the report that it's spitting out is in fact factual and correct. Okay? Anything else? No? Yes?
Where do you pull packets from? Do you pull those from the same place or off the servers?
So at City we have multiple locations. We sometimes we put capture agents on PCs that we control. Sometimes it's TCP dump or snoop or IP trace. Sometimes it's a sniffer that we have in a common location that we span the ports to. So it depends on the situation. Okay. We have these sniffers deployed throughout the data centers that we move around and take packet captures as required. But oftentimes, Wireshark at the client, at the proxies, firewalls, they all have TCP dump built in, right? So those are good places to start. And in most cases, you don't need full packet captures. So don't get in the habit of doing full packet captures. All you're going to do is waste space. Most TCP analysis don't require full packets, okay? Unless you're doing application level troubleshooting, yes? Yes, it's a big sniffer. It's constantly running a huge terabytes of data. Shark Appliance is one. There are other vendors that have, big honking sniffers, if you will. Some people use laptops with Wireshark running all the time, right? So it depends on your budget and how creative you are, I guess. If you will. Okay. Anything else, guys? Okay. Thank you very much.